This is Ray's Super Magnet Generator. You can see the large neo magnets, one there, one back there, and in the center we have a coil. It's about a 5 ohm coil. There's a bump switch here, and that engages the load, and there's the power from the power supply. We have it's a 6.2 250 0.25 amp light bulb, but we have right now 18 volts. It's showing bouncing between nothing 0.00 and sometimes it'll do a 0.01, so I'm calling that split the difference 0.005. so when we multiply that together we get 90 milliwatts. 90 milliwatts is firing the light, pulsing it. You can see how the brightness is there. You can kind of remember that. We're going to show a similar wattage on direct resistance measurements. Okay, we'll do that by bringing this down to 2 volts. And we'll go ahead and take it out of the generator, and we'll go ahead and put the light on. Now you can see the light lit. There. Not as bright, and yet we're using more power. And power is voltage times current, which is 100, or I'm sorry, that'd be 120 milliwatts. 120 milliwatts. Here. 120 milliwatts. You can see that that's not as bright as what we had before. Let's bump it up a little bit. We'll go up to about 3. Okay. And there's the brightness there. You see the reflection on my hand, that's what to go by. It's still not as bright, and I'll show you there at the end, but it's taking in 3 at 0.08, that's 240 milliwatts, 240 milliwatts. Okay, let's go up to 4, and then we'll go back to the generator. It's a possible over unity generator. That's what I'm going to be showing here. The differences between in the generator and out of the generator. There you go. And that's the brightness now. If I can get this down here. So, sorry about that. So that's about, I'll go ahead and we'll try this again. Sorry about this old camera. Okay, there's about it's 400 milliwatts. 400 milliwatts. See the reflection on the back. Okay, 400 milliwatt. And I can tap that and get a better idea too. The brightness. Okay, now we're going to go back to the generator, putting it back in to the generator circuit. Oh, I'm sorry, that's the oscilloscope. Okay. Let's go ahead and we're going for power. So We have to do this indirectly. That's why I'm using a light bulb, and I'll explain that later too. Okay. At 18. Close enough. Okay, now I'm going to put my hand behind it. See how much brighter. So we're using less power, obviously. We're below 0. Really, every once in a while, there's the 1. So I go ahead and say that's 0.005. So when we use that 0.005, we had 90 milliwatt. 90 milliwatt is much less than the 400 milliwatts. So something's happening in this pulsing. If you notice, I'm using about 2 cycles per second. What I'm saying in a capsule form is that when a coil, an inductor, the field collapses, there is more power coming out than it was to make it. So that's a pretty far claim, but these measurements are doing some verification. Also, formula-wise, we have for an inductor current. E is the voltage, XL is the inductance, F is the frequency. So why hasn't this been noticed before? Well, I believe because inductors have been used in 60 cycle systems, thousands of cycle systems, and it doesn't show up. If you put a say 60 in where the frequency is, you'll notice that the current goes way down. If you put 2 where the frequency is, like my generator, the current is going to go up. What is it doing though? Okay. I'm going to show that my theory, and I'll be back in just a second. The theory is that a collapsing field puts out more power than it takes to make it. But this collapsing field has 2 vectors to it. One is electrical, as to be expected. We did that. The other is what I call stuff, which I named as being a very unusual energy. This is the second vector. The electrical vector can be measured with conventional meters. We did that. But this stuff vector cannot and must be measured indirectly. And that's why I'm using a light bulb. The higher the frequency, the less the current. We want maximum current to grab this stuff. It's a raised magnet, supermagnet generator, works at about 2 cycles per second. Because the stuff needs to be measured indirectly, 2 methods have been devised. This is the bulb, the next one will be the motor. Be back in a second. Okay, we're going to do some indirect testing with a small DC motor. I have it set at 2 volts. Okay. We will see what it does. Just kind of wiggles the bolt. So let's see how much current that's taking. Taking about 0.17. So that's about let's see, 0.17, 16. We'll go 16. 0.16 times 2. 320 milliwatts. Okay. Let's bump it up a little bit. The voltage now, I'll bring it up to 2.8. Well, let's see what happens at 2.5. 2.5. That's a pretty good bump there, huh? Okay. Okay, let's see what it's doing as power requirement. 2.5 volts for the power. Multiply that by 0.22. Okay. And we have times 0.22. I have by 550, somewhere around 550 milliwatts. And the bolt goes like that. Okay, we'll go back and let's go a little bit higher. 2.8 volts. That's what I had earlier. It could lift it. Okay, see what that does. Yeah, just barely lifted it. And that's using 0.25 amps. So 2.8 times 2.5. So I have like 700, about 700 milliwatts to lift it. So we want to remember that number, 700 milliwatts to lift it. Okay, I'll be back and we'll put it in the generator circuit. Okay, we're doing some comparison work with a small DC motor. You can see it's drawing very, very little. I call it, every once in a while it'll go 0.01, so I split the difference, 0.005, just on the air of caution. And that gives me about 70 milliwatts. So before we had 700 with the resistance check milliwatts, and now we're going to see what the bolt is doing with only 70 milliwatts, but it's in Ray's super magnet generator. See, it's obvious that it's much more powerful. So in summary, what I'm saying is this unseen, unmeasurable stuff has a lot of current oop to it. You can't measure it, but it's in indirection measurements, light bulb and bolt. I'll be back in just a little bit and finish up. I put the light bulb back in the circuit, and you can see it's bright. We're using the almost no power. Okay, here's my numbers again. This is for the motor. So for the motor, it was like 700 milliwatts with the resistive load having a certain brightness versus the 70 milliwatt. I'm sorry, for the motor, the lifting power. So there's quite a bit of difference there. Okay, thank you so much for watching. If you want to get a diagram and some information, everything that I put in here plus a little bit more is included in my packet. You can see the description area, and this is it. Thank you so much for watching. Have a good day. Happy inventing. Make every day count.